Hello everyone. So today we'll be learning something new. So that is about earthquake designing. So first of all, we need to know how to design a earthquake thing. I mean, the point is, first of all, we should know that the earthquake is not a load. So it is some kind of an inertial force that is going to act on the building or something like that. So that is one thing. And usually what happens with earthquake is we should know how earthquakes affect. I mean, first of all, we should understand how it works, or how is the earthquake forming, or how is it going to start, where is it going to start from. So for that, you guys can see an image in here right now where there is we have mentioned what is surface waves and body waves. So usually what happens is this point is there, right? What we do is here there is a thing called as epicenter, and here there is a place called as hypocenter. So usually what happens at this hypocenter level, where the two material collides, or maybe there is a formation of kind of a force or something like that, maybe some kind of a shear, just like this, some kind of, there will be a movement just like this. One will go to the top and the other one go to the bottom. So due to that, there will be a formation of fault rupture, and due to that, there will be a body waves and surface waves formed. So usually what happens is, first of all, you guys need to know what is P waves and P waves, S wave, and L love waves and railing waves. So P waves is like push and pull. So what happens is this one part and this one part, maybe it'll extend, or it'll compress. So that is one thing. And here in secondary waves, what happens is it will go to the sideways. And as you guys can observe in here, here what happens is the whole body will move. The whole body will move. And even in this case also it is the same. The whole body will move. But in this case, love waves, it is only at the surface level. So you guys need to understand that out. So even here it is the same. Only at the surface, the movement will be there. So this wave and this wave, it is called as surface wave. So that is how it works. So here you can see here whatever is acting in here, right? These are called as surface love waves and railing waves. So only those two will act at the surface waves, and these whatever the inside part is there, no, inside here, that is called as hypocenter. So there you can see that it is P waves and S waves, and to the top there is a thing called as epicenter. So that is one thing. And this distance was there, right, from hypocenter to the epicenter. Whatever the distance that you guys can see, whatever the distance it is, that gives us exactly like how much the intensity was, or how much the distance was about the earthquake thing. So and it will damage the earth structure. So now I think you guys have clear with how the earthquake works. Due to the fault formation, there is a earthquake. I mean, due to the fault formation, there is waves formed. So those are two waves, surface and body waves. And due to that, there will be a movement in the earth, and due to that, the structure will fail, or maybe there will be movement, something like that. Okay, so once this concept is clear right now, you guys need to understand how do we design earthquake load. Usually this is the very important thing right now when it comes to a structural engineer, or or any like a civil engineer perspective. So we should in today's world, it normally how it works is, um, what happens is we need to design resist earthquake build. I mean, we need to design earthquake buildings. These days it is mandatory to do it because there are a lot of earthquakes going on, and within 10 to 20 years, people will ask you to do this earthquake design. So you should know the concept how it is done. So usually what happens is, so imagine there is a frame structure like this, and there is a movement. So there is a movement due to the force. and this movement is there, and there is a mass in here, and there is a force acting. So what happens, this, because due to this force, there will be a movement happening in this structure. So we can write it something like this. So V is equal to elastic base shear, so shear divided by response reduction factor, something like this. So I'll come up with what is reduction factor, all those things in the upcoming section. But you guys need to understand this. So what reduction factor normally, I'll give a picture about it, like a small idea about it. How it works is it reduces the load based on the building's ability to absorb energy. So it will, usually what happens, a building, whenever there is a load acting, beams, columns, even slabs will take some kind of a load, and it will distribute to the columns and even to the beams, and from there it will distribute uh, to the base. So usually that is what this means about reduction factor. And shear force, what happens is that is what we are going to design. This is a base shear. Okay, so base shear is equal to elastic base shear. Elasticity, I'll come up with that now, how it works. So usually just imagine, just take a rubber band, okay? And sorry, let's first take with a brittle structure, okay? Just take a chalk and cut it down. It'll break easily, correct? And if you take a rubber band or something like that and you try pulling, there is some kind of an elongation, one point of elongation where there will be a small point of rupture, something like this. This formation is there, right? It will take time to break. So that is the thing. That is how an elastic thing works. Even with the steel member also, just take a mild steel. As you guys have, I think you guys have done a lot of experiments where you guys check out the tensile strength. So that is one point where it ruptures. That is an elastic point. So that is how it works. So I think reduce earthquake load. There's a formula given in IS 1893 1893, and I'll be coming up with that in the future classes. So this is one thing. So I think you guys have understood. So usually what happens is when the load is too much, we are going to reduce the load as much as possible. We need to check out how much the load can be transferred to the soil, because this is connected to the soil, and this soil is there, no, this sand area. That is usually what happens. We are giving this a fixed support, and that is going to transfer some kind of a load to that, to the base. So that is the reason we are going to reduce the earthquake load. So that is one thing. Next, ductility. Right now, I've explained you guys how it works. I've taken an example of a chalk and a steel member. A rubber band or maybe a steel member. And you guys know at one point of time, it will resist as much as possible the ability of a structure to deform without collapsing. So what happens is in IS 13920, there is a ductility required. Whatever ductility is required, it is given in that. So in the upcoming future classes, I'll be explaining that too. So that is the other one thing. So IS 13920. So this is other code book. Now, next, it comes to be redundancy. Usually, what happens with redundancy is having multiple load paths or frames that can carry load even if one fails. So, usually, what happens, this is a beam column, and this is a column, and this is a beam. Okay, and usually, what happens is just imagine, yeah, I'll remove this off, only one is kept. Don't you think load will transfer? So this is a load acting. In this case, however, the load will transfer because there are two supports. But don't you think there is a load transferring even through this, because there's one member in here? Yes, it is possible. So that is thing. So what happens is how we need to design it. Like we need to design it such a way that Maybe if one of them collapses, imagine this to be a column, and one of the column collapses, but still the whole load is there, right? That should be distributed to this. It should have that kind of a capacity to take up that load. So that is how it's going to work. So that is called as redundancy. Okay. So it is better to give more columns, beams, braces, so it will turn the building safer. If one frame fails, the other one should share the load. So that is how it goes to work. Next, overall strength. Overall strength is the structures overall capacity. I mean, the actual capacity is more than what we have assumed. So usually what happens is we will be designing for, if imagine we are going to design it for 300 kilonewton, but if the material is good and the detailing is very good, we have given the proper bending, I mean development length, and if the concrete we have used it in the right way. Maybe if you have, see, usually what happens is if you're giving no M20 ratio, it will give us a strength of M25. So that is kind of a strength that we achieve. And even in the strength of the steel also, it is the same thing. If it is a 415 thing, Fe415, we get more strength, or maybe these days even 550D has come. So ductility, so that is how it works. So these are the things that comes to like picture. So now what happens is, so actual collapse strength should be more than the design strength. I mean, it will be more than design strength. That is how we are going to design. So overall, these everything matters. So redundancy, you guys have understood, um, and overall strength. So actual strength plus, I mean, it should be more than the design strength. Design, and usually that is true because that is how we are going to design. Because normally what happens, every way you consider, we are going to give some kind of a factorial load. So usually when it comes to earthquake loading or maybe any kind of a loading, what happens, live load plus dead load is given, and we give a factor of safety of 1.5. Even in the design cases also it is the same thing, we give 1.5 or maybe sometimes 0.75. Some kind of like a factor load is provided in any sense whenever we are going to design any kind of a building. So this is how it works. The overall thing is equal to the earthquake load. So this is how we are going to design a structure. If you think the video was helpful, please do like, share and subscribe. Thank you.